Hello again, folks, in 113. Today we're going to be starting with, well, it's really a new chunk of material, but it is still in Chapter 5. It's the two sections that we skipped over from Chapter 5. And we're specifically going to be covering Section 5.4, right, which is about irrational numbers. Right. And normally I don't write the heading, I know. But I don't know, it's just such a peculiar sort of word. I figured that it was worthy of emphasizing. So, here is the calendar. Today is Thursday, March 25th. So, as per the schedule, we are doing section 5.4. Okay. As I mentioned, it's just those two sections we'll be having from chapter 5, the ones that we didn't get to before test number 2. All right, test number 3, which is forthcoming, should be May 4th, right? And you'll have, again, a chunk of those homeworks in my lab that will be due by that evening, May 4th. You should see it already in Canvas. Anyhow, the packet that I have for you today looks like this. There's a diagram. You might have this already if you had been following along to this point. I just want to give you this again because I want to add information to this side of the chart. Okay. Again, we're covering irrational numbers, so I want to emphasize that. Here's a reference in terms of the perfect squares and perfect cubes. You're primarily responsible for this, but this concept also exists. The numbers that you see here in purple are the perfect squares, right? 1, 4, 9, 16, 25, and so forth. This is something that, again, in the long run would be good to memorize. But if not, at least you have a reference. This is the same information, really, but from the opposite perspective. All right? This is when you're talking about square roots. Now, square roots are just one of many types of roots. There's cube roots and fourth roots. You can't memorize them all, but again, it would be practical to know or recognize that these numbers in purple here are perfect squares, and if you take the square root of them, you get a whole number answers. And if they're whole number answers, then those things are not irrational. They can be written as a fraction. This is basically the strategy for factoring radicals. There's another name for this, and in fact there's another rule in addition to it, the product rule and the quotient rule for radicals. All right? But this is the basic strategy, how you want to factor if you can. All right? There are some problems that you can't. All right? Anyhow, if you're following along, do print this out and we'll begin. Okay, section 5.4. All right. Let me turn on my projector. If it cooperates, and then we'll get started. Okay. Boy, I didn't turn on my thingy here. Okay. Bear with me. Okay. Let me scoop this over just a wee bit. There we go. And minimize and blow this up. Okay. All right, now previously we had discussed in relation to this diagram rational numbers. Section, I want to say, at least it was maybe 5.6 or earlier. If not 5.6, then section 5.3, 5.2, and 5.1 were about this category, if you will. All right, the rational numbers. Now, I think it's important just from a practical standpoint, and I would encourage you to impart this to your own students. All right, make this distinction What is rational essentially is something that can be a fraction. It may not start out looking that way, but it can be converted to a fraction style of writing. A ratio of two numbers. And therefore, what is irrational, which is really the subject of today, let me get my mouse out of the line here, are things that really can't be a fraction. That makes them special, basically. Okay? That is as concise a definition as anyone could give you in terms of rational or irrational, right? That is the essence of what their difference is, right? Why irrational? Well, it's for two circumstances that go on. If you analyze the figures in question, there's some popular numbers that you would recognize, right? They are, if in the form of a decimal, they're non-terminating, which means that they're infinitely repeating, and they're infinitely stretching, and non-repeating. I mean that they don't have an obvious pattern, right? Now, famously, the irrational numbers that everyone knows probably is something like pi. Right? Pi we are taught to memorize, right, if we use it as a decimal, is something like 3.14. But what you have to realize is that that's really not quite correct, right? That's just the first three digits of pi, so it would be more appropriate to put a squiggle about equals, approximately equal to symbol, when you say that, all right? If you go a little bit further, if you have a higher degree of precision, it would be 3.14159, all right? And that's as much as I have personally memorized. But it is beyond that, even. Anyhow, if you analyze it, it is non-terminating, meaning that it stretches into infinity, and it's non-repeating. It doesn't have an obvious pattern to it, right? If it doesn't have an obvious pattern to it, then there isn't a technique that I'm aware of anyhow that you can convert this to a true fraction. All right, there's been many attempts in history, and that's really why this was discovered to begin with. All right, but it's a mathematical impossibility. It's a special number. All right. To be very spiritual, like, it seems to be that this number is important to the universe somehow. Right? And there's other numbers too that you'll see. Square root of 2 is another example of a famous irrational number. Right? It's approximately 1.4142 something into infinity. You can't memorize all of its digits, although I have a friend actually that knew it, pi at least to like 1,000 places or something like that. Brilliant man. Then there's E, another famous irrational number, which is something like 2.7182 something into infinity here. All right, now, you're not really responsible for something like E, but it's of this category, and it is famous, all right? And if, again, to be perfectly, this is silly perhaps, but to be spiritual about something numerical, all right, these numbers are important, all right, to the universe, all right? Specifically these two, pi and square root of 2, something like that. Where do they originate from? Well, they come from geometry, really. Right? And you will likely bump into them in the subject of geometry. Right? E, although you're not responsible for it, E comes from a different subject. It comes from finance. Right? Basically, it comes from calculating interest. Right? And nonetheless is very important. It is a foundation of calculus. So it's something that we should pay homage to. Okay? Anyhow, we're going to discuss pi and square root of 2 and things that are related momentarily. All right? Anyhow, just bear this in mind, all right? What causes something to be irrational? That it is these two conditions, non-terminating and non-repeating, which means there's no pattern essentially, simultaneously. All right? Things that are terminating or repeating, all right, those can be written in the style of a fraction one way or another. Right? So, but if you are simultaneously non-terminating and non-repeating, then you are likely to be irrational. Imaginary numbers are yet another category, but you're not really responsible for that. So our focus is really just here in the family tree. Okay, so moving on. Let me ditch this. We'll discuss pi and the square root of 2 a little bit more in-depthly. Just for the sake of space, let me do this. Go to partition. Right, we'll talk about these two things. Where exactly does this symbol come from, pi? That's a very stylized pi, and I'm probably not even drawing it correctly, but I'm going to give it my own little flair here. Looks like a 2, right? It's not, it's pi. Something like that. Okay, versus the square root of 2. The superstars here, and someone else much smarter than me had coined that phrase. The superstars of math, pi, e, square root of 2, 1, things like that. They're very important. Basically, our awareness of pi, right, as a number that is important, comes from the attempt to form a ratio, i.e. a fraction, of circumference, and perhaps I will write this in a different color. Circumference over diameter. Now we're probably, all of us, familiar with this formula. Right? We're familiar with the circumference of a circle is equal to pi times the diameter. Right? And from a practical standpoint, it's arranged this way, right? That it is set equal to c. Right? In theory, you could algebraically rearrange it to solve for any one of these things, but it's usually arranged as such that c is by its lonesome on one side and pi is on the opposite side with diameter. This is in reference, of course, to a circle, right? If you know the dead center of a circle, and there's a line that goes through it, the line that goes right through the center to the edges, to the edge really, that is the diameter, of course. And often diameter is abbreviated by the letter d. Right? If you were to measure instead of across the center, around a circle in its entirety, that would be a circumference. Anyhow, physically, if you had any size circle, you could, in theory, measure the distance around the circle. This is a badly drawn circle, of course. and the distance across it. The thing is that it's a measurement, and because it's a measurement, it's only as good as the tools and the person. That is, it's only as reliable a calculation or a number as the person doing the measuring and the tool itself. Anyhow, the Greeks and probably the Egyptians before them really were interested in this arrangement instead. Right? The circumference divided by the diameter. Because what they had noticed is that for any size circle, whether you had a very puny circle or a very large circle, if it was a true circle, right, this seemed to be approaching the same number no matter what, right? Consistently doing these measurements, measuring the circle's outer edge all the way around and measuring across its center, which is a difficult task, right? I dare you try it, it's not too easy, all right? You will start to see the same number over and over and over again, all right? Now, again, the measurements are probably not really accurate, right? They're accurate to a certain margin of error, all right? But they keep producing this number being something close to 3.14. If they had better tools and more reliable human, eyes and hands to measure, this would be accurate to a greater degree of precision, right? Anyhow, it's a futile effort because we know now it's irrational, right? And by definition, what is irrational can't be really a fraction, right? So it's one of those numbers that will be infinitely stretching and it won't have a pattern, right? 3.14159, whatever it is. There is no obvious pattern anyhow, So it comes from our attempt at trying to write a fraction, right? Square root of 2, similarly, comes from something else. Right? Our awareness, still geometry, comes from trying to solve for hypotenuse. Right? Now, again, we're probably familiar with that phrase, and if you're not, don't worry. Right? This is in reference to a certain type of triangle, right? Specifically, a right triangle. This formula, known as Pythagorean Theorem, is specifically for right triangles. Again, this is a badly drawn right triangle, but a triangle is by definition an enclosed figure in a plane that has three sides, right? And so if we maybe label the sides, let's call this A as in altitude perhaps, and B as in base or bottom, right? Then, and just sticking with this alphabetically, this dimension across from the box would be naturally C, right? Another name for this dimension that is across from the box, which represents a 90-degree angle, by the way, is hypotenuse, right? The hypotenuse is the fancy way of saying longest side, right? Now, famously, the formula that we all know and love is this: a squared plus b squared equals c squared. Okay? That's the Pythagorean theorem, all right? Its purpose is, again, to solve for any one of the three sides of a right triangle specifically. It only works for right triangles, all right? You'd need some other form of this if you had some other situation. Anyhow, a squared plus b squared equals c squared, right? The basic gist of it is that if you have 2 out of 3 parts, 2 out of 3 dimensions, you could figure out the third one algebraically. Now let's just say hypothetically that you had this situation. That you had a right triangle with 2 measurements that are exactly the same. This dimension here being 1 and this dimension being 1. It's not drawn really perfectly, but that would force the situation here to be what number, right? If you have basically 2 legs that are equal size, right? That would produce a certain number here, right? I should mention also, these dimensions that are perpendicular to one another, they're referred to as legs. This is a leg, and this is a leg. And they're interchangeable. If you wanted to change the labeling from A to B and B to A, vice versa, switch the position of these labels, that would be perfectly fine, right? Because they're the same type of thing. This is a leg and this is a leg. The one thing that is non-negotiable is the C value. That's the hypotenuse. So you really cannot interchange that with either of these other 2 dimensions, okay? So just beware of that. Whatever number is here, that has to go in place of C if you happen to be given that thing. In this scenario, I'm looking essentially for C. You may not realize that, but if you convince yourself, always look at the box. You could figure it out, right? I always say to myself, all right, well, if this is where the box is, right, the C value would have to be directly across from it. It's always across from the box, right? Therefore, you could call this A and that B or vice versa. I like to stick with this logic. This is A is in altitude and this is B is in bottom or base, right? Let us say that I insert these figures into the formula. I'll put it here. A squared plus B squared equals C squared. They coincidentally are the same dimension in this scenario. So if I put a 1 in here and a 1 in here, how would that work out if I straighten up the arithmetic? 1 squared I'd have to do before adding, according to the order of operations, because I'm just simplifying one side here. So that would be 1 plus 1 essentially, and over here we'd have C squared. Okay. If I just take the time now to add these, right? Obviously, what is 1 plus 1? It's just 2, right? And a person with maybe perhaps lacking experience will go, oh, good, right? Done, right? But are you really finished if you have you've solved for a letter that has a degree of 2? Normally, there's no number written here, right? When you're done, when you finish solving for something. What you would end up doing in a scenario like this is basically the following. You would take the square root of this C squared for the cancellation effect. That produces. Remember, opposite operations induce a cancellation effect. So this would cancel this essentially. And then, as a matter of legality, if you've done it here, then you would be obligated to do it here as well. And that means that the C value that you would be looking for in theory would be equal to the square root of 2, right? Now, as for square roots themselves, right, they're kind of a turbocharged, super-duper form of division, right? In the same way that squaring is kind of an amped-up version of multiplication. The question of square root is basically this. A square root asks what number multiplied by itself makes the number underneath the radical symbol, the inside here. In this instance, you would ask yourself, what number times itself would produce 2? Is there any number times itself that would produce 2? There isn't. The reason why I'm saying that this is something like division is because it shares a similarity in terms of the operator symbol here. If you just had a problem like this, 2 divided by 1, right, you would just say 2. You would put the quotient here, you would put the divisor here, right, and the inside would be referred to as the dividend, right? When you're taking a square root, there's no reason to put a number here and a number here, because in theory, those two numbers would have to be identical, right? Normally what they do if there is a solution is they would put an equals and then write whatever it is after the fact. Anyhow, the bottom line is that there is no number times itself that would produce the inside here. There's no number times itself that produces 2. Not that is a whole number anyhow, all right? So this is part of that category of irrational numbers, right? It will be infinitely stretching, and it will have no obvious pattern to it, right? All right. So we add it to the pile, right, of interesting numbers that seem to be important, right, to the universe, right? Anyhow, the analogy that I was trying to get at was that we're aware of this because of a certain mathematical problem. We're aware of it specifically because of the Pythagorean Theorem, the attempt at trying to figure out how long a 1-by-1 triangle would be in terms of its hypotenuse from geometry. We're aware of pi because of the attempt at trying to write a correct fraction to define what pi actually is, what this ratio is, all right? Both of them are futile efforts, really. You're never going to get an exact answer. The exact answer is just this thing symbolized. It's just not very satisfying because we're so used to decimals, right? If you had a calculator, I would bet that a person would intuitively go, well, I'm just going to get my calculator to tell me what the square root of 2 is. And your calculator can give you a very high degree of precision. But just realize that even though it says 1.41, whatever it is up to the edge of your screen, after that point, it can't tell you anything else, right? And there is an infinity of numbers that trail it. Right? Why? Because it's irrational. An irrational number is infinitely stretching. I have to clean up my brush, forgive me. So, we have these interesting types of numbers, and they come from geometry. Right. And then later on through human history, we will add to them these other famous constants like this, like E, for example, which come from maybe other subjects like finance. All right. Now what I want to show you is this diagram that I've made here. It's a reference of numbers that you can have on hand when you're doing your work. But it would be good in the long run to try to memorize. When you memorize information, and don't let anyone ever talk you out of memorizing anything, it makes you more strategic. You know, you're building up a frame of reference, basically. Something to compare to. And in this section, that would be very practical. Oh, tenacious blue. I should not write the markers that are sticky like that. Take a gander at this, and I'll adjust the light. Okay. You've heard probably this term, perfect squares, maybe at some point in your life, or perfect cubes. All right. What is it referring to? A perfect square is basically referring to the area of a square. Right? And although you're probably not responsible for this now, this next step in the train of thought would be perfect cubes. Perfect cubes are referring to the volume of an actual cube, right? A three-dimensional square, if you will. All right. Now you know that if you found the area of a rectangle, right, that it's famously length times width, right? They take the time to give it two different labels, a length and a width. But that's for a rectangle, you know. A square is a type of rectangle, but it's a more precise rectangle. It's a more specific condition. So if you were to find the area of a square, there really would be no reason to give it distinct labels of its side dimensions, because they're the same number, whatever they are. So it would be the same as saying side times side, all right? And if you wanted to, you can abbreviate that using an exponent, right? What's the abbreviation for s times s? S squared, right? Let us say hypothetically that you had an area given to you, right? An area of 1, right? What that would mean is that the sides would each be 1 here and here, because 1 times 1 would make the area of 1, right? And so forth. If you had an area that was 4, right, what would that mean? It would mean, since it's a square, all right, that the side dimensions would have to be identical. It would be 2 times 2, all right? If you had an area that was 9, right, cut up like this, then the side dimensions would be 3 times 3, right, and so forth. These things, again, in purple, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. They would be good in the long run to memorize, because then, again, you basically have a frame of reference, something to compare your judgments to. Right? When you're trying to make a judgment call, it's nice always to have a frame of reference. I hope that's visible. My black is dying. All right. Anyhow, similarly, if you had a volume, which is a three-dimensional area, if you will, the inside of this cube container, each of its dimensions would be the same. So rather than calling it length, width, and height, we would just call it side, side, and side. It would be those three things multiplied in sequence. So a volume of 1 would have a dimension of 1, 1, and 1. All right. A volume of 8 would have a dimension of 2, 2, and 2. A volume of 27 would have a dimension of 3, 3, and 3. All right. That's where the phrase squares comes from, where the phrase cubes come from. And these are perfect because they have the exact same side dimensions. They were also, you notice something very nice about them. They are whole numbers, right? The side dimensions are whole numbers. Right? And the original area, of course, is a whole number. Right? This other slide, which I'll show you rather quickly, this one, is the same information, right, really, but it's from the perspective of square rooting, right, or cube rooting or fourth rooting. I'll get the gobbledygook out of the way here. There's this symbol that looks like a check mark. Unfortunately, it's not really complete. It should have a little hat on it, like so. And then whatever the number is would be on the inside. That is the symbol for square root. I put this little thought cloud up here because there's different types of roots. Right? There's square root, cube root, and fourth root. And unfortunately, when it comes to square root, because it's kind of the OG, it's the original concept, they don't really put the number 2 in here. It wouldn't be wrong if you put that there. It would make things extra clear, but it's the original concept, so they don't really do that. They, whoever they is. But for cube root, to distinguish it from square root, you really have to put the little 3 tucked into that little check mark. All right? And similarly for fourth. All right? Anyhow, if you took the square root of perfect squares, the square root of 1 would be 1. All right? The square root of 4 would be 2. The square root of 9 would be 3. and 4 and 5 and so forth and so on. And what is interesting about that is that these are all whole numbers. Okay? Notice that the outcome of each of these square roots are whole numbers. They're not decimals. Right? And because they are whole numbers, if you really wanted to, you could write this in the style of a fraction. You could make this 1 over 1. You could take this 2 and make it 2 over 1. You could take this 3 and make it 3 over 1. You could take this 4 and make it 4 over 1. You could write whole numbers in the style of a fraction, and therefore those are rational. Notice what is missing from this list. All right? If you analyze the perfect squares, 1, 4, 9, 16, 25, what is not in here? What is missing from this list? There's no square root of 2. There's no square root of 3. How come? All right? The square root of 2 is not rational. When asked the question, what number times itself makes 2, there isn't one, right? Well, if you ask yourself the question, what number times itself makes 1, it would be 1 itself, right? What number times itself makes 4? 2 times 2, right? What number times itself would make 9? 3 times 3. The square root of 2 is not in this list because it's not rational, right? And since it's not rational, it can't be a fraction. Right. So just bear that in mind, okay? Now, the last thing before I give you some, now, there's a bit of more theory here for a moment. I don't want to bore you, but I want to show you something else for reference. What is going to be important in the long run, even if you're teaching grammar school children, there's kids in K through 5 or maybe junior high, middle school, it would be good to give them this information eventually, because it will be useful when they get to algebra. Right? And algebra, even if it's not anyone's favorite subject, right, is certainly a subject that anybody can handle. Right? You have to go into it believing that because it's true, right? All right. We have this concept. We have been developing since the time you first entered school. All right, this concept of operations, right? It's a funny way to spell that. Operations are basically things you do to numbers. That's not very elegant to say it that way, but it's true, right? Stuff you do with numbers. Right? Now, there are operations, and then there are opposite operations. They're opposite. Now, famously, you come to school basically, hopefully, and that isn't always the realistic, but the ideal situation is you come to school with a basic number sense. You can't count, right? And then we teach you a slightly more sophisticated form of counting, which is essentially what? Adding, right? That's the operation, the thing that you do with numbers, you add them, right? And then eventually you are taught the opposite concept. What is the opposite of adding? Subtracting, right? Further down the pike in your life, right? If adding is a slightly more sophisticated form of counting, multiplying is a slightly more sophisticated form of adding. It's adding very efficiently. And that's the kind of thing that you should definitely encourage a kid to memorize, multiplication tables. It's imperative. No matter what anybody in authority tells you, don't make them do that, baloney, forget that they told you that, make them memorize stuff. All right? It's like spelling, right? You know, you need a foundation. You need a frame of reference, right? to learn more complicated concepts, right? Anyhow, there's the concept, the operation, the thing you do to numbers, multiply them, and then its opposite, division, naturally, right? Usually in the United States, I can vouch for this, that's usually around maybe 5th grade or 6th grade, right? They teach you a slightly more sophisticated form of multiplying, which is to raise something to an exponent. So there's no real symbol for this, so I'm going to just sort of draw a question mark and then a little superscript 2 adjacent to it. So you have something that is squared, right? It's still a kind of multiplication, it's just a more precise form of multiplication, right? Well, there's that operation, that stuff you do with numbers, right? And then there's its opposite. And that's where we are at now in the conversation. We have the square root of something, right? No book will ever put a 2 here, all right? But I'm going to, because I want you to see the relationship. This is squaring, and this is essentially square root. And in the same way that this is squaring is an amped up version of multiplication, square root is kind of like division, but it's a very specific kind of division, right? Where the factors, the thing that makes the number here, are identical, right? Okay, they have to be, otherwise it's not correct. Because I'm short on space, I'm just going to add some stuff here and here. The thing about radicals, which is what that is referred to as, and raising things to an exponent, is that there's an infinite number of them. You really can't memorize all of them, but you can be familiar with the very basic ones. Here's the next one after squaring, which is this, right? Raising something to an exponent of 3, that's referred to as cubing, right? It's an instruction to write whatever this base number is, 3 iterations of it, and then multiply those 3 iterations. 3 clones, if you will. So something times something times something, right? Versus in the case of squaring, something times something. These are referred to as iterations. I like my own phrase for this, clones, if you will, of whatever the base is. And then you multiply them, right? Well, if we have this concept of cubing, my shirt keeps falling out. What is the opposite of that? There is cube root. And in that instance, because they have to distinguish it from square root, which again, they never put the 2 there, all right? They have to put the 3 there, all right? Otherwise, it would be confused. This would be referred to as a cube root. If square root is asking the question, basically, what number times itself makes this number that's sitting here, then cube root is asking you, what number times itself times itself times itself, 3 clones makes that number there. Right? It's kind of a form of division. And there would naturally be a 4th root and so forth. All right? Anyhow, the reason why I'm trying to really emphasize this idea of operation and then opposite operation is because when you get into the subject of algebra, and sometimes inklings of algebra make their way into your life around 5th or 6th grade in the United States, in order to solve algebraically, algebraic equations, right? What do you end up doing, right? You employ opposite operations. Kind of illustrated this before. Why? What happens when you use an opposite operation, opposite to whatever is given to you? It basically causes a cancellation effect. That's really the whole practical usage of it, all right? So when we had that problem of Pythagorean Theorem earlier on, in order to get it to be just C, right, just the letter C and not C squared, I had to square it, I had to raise it to, pardon me, plop a square root on it, because that is the appropriate opposite operation. Right? Now, let me give you some terminology here. When it comes to roots, there's some terminology that is good to know. That is when we're dealing with situations like this, and you guys are primarily responsible for square root. If you had a situation like this, the square root of 25, right? That's how you would read it in English. The square root of 25. And it's a question, naturally, right? The individual components that make this group of symbols here, let's see if this light helps. They have names, right? They're not always important, but it's good to be able to refer to them if you have to give somebody an instruction, so allow me, please. Whatever is the identifying number that would be here, this would be referred to as the index. All right. And the index is essentially the type of root. In the case of square root, again, nobody ever puts a 2 here, but if they did, it would be better perhaps, because then it would be very clear what type of root you're dealing with. Right? Again, it's the original concept though, so the 2 is, it's sort of like ones get left out and decimal points get left out and zeros get left out, right? If it's a convenience not to write them. Anyhow, that is referred to as the index, and it is essentially the type of root. The number, or whatever expression that is underneath this checkmark box, is referred to as the radicand. Right? Think of the radicand as basically being the guts of the radical, right? The entrails, right? The intestines, and other internal organs of this thing, right? The symbol that is the box, this symbol is referred to as a radical symbol. So an alternative to referring to these as roots is to refer to them very often as radicals. Because it's radical, man. All right. Anyhow, the whole thing could also be referred to as a radical, right? The square root of 25. Well, what is the square root of 25? That's what the question, that is really how you would read it in English. What is the actual answer to this? It's asking you, essentially, what number times itself makes 25 in this particular case. Right? If you could conceive of identical factors, and they would have to truly be identical, what would they be? What number times itself makes 25? It would be 5 times 5, right? So therefore, the answer to this is, in fact, either, well, it's technically there's 2 answers, but it's 5, really. Now, just as a technicality, let me share some fun factoid with you about radicals here. There's 2 possible scenarios. Right? If we were to answer this question completely, thoroughly, right? what number times itself makes 25? One of them has already been specified. In theory, it would be 5 times 5, so we'd say the answer is just 5. All right? But there is one other combination of identical factors that would in fact make this number 25. Right? And we are aware of it from integers. Right? It isn't written, but this is in fact a positive 25. Right? So what combination, alternatively, of identical factors, and they have to be completely identical, would make positive 25? We have, in theory, isolated this possibility. Positive 5 times positive 5 would make positive 25. But what's the other pair? All right. It would, in theory, be negative 5 times negative 5, because a negative times a negative also makes a positive. So this is, in theory, another possibility. Negative 5. That is why oftentimes when you see the answer written in the back of a book or elsewhere, they will sort of write this as the outcome. They will say, what's the square root of 25? It's plus or minus 5. It's a way of not having to write positive 5 comma negative 5. They will simply stack the symbols. Anyhow, for practical reasons, we don't really pay much attention to the negative, certainly not at this level of math, right? And this has a specific name. The positive incarnation, the positive answer, which is the favored one, is referred to as the principal square root. So assume when you're doing your work in my lab for this class that you're looking for the principal square root, namely the positive answer that is a possibility, not the negative one that theoretically exists. It theoretically exists, but it isn't necessary. Okay? All right. That's the terminology. All right. Now the last thing before we do some examples is an overview. Just to show you what we're going to be doing. And then we'll get busy. Okay. Here is basically roots, radicals, whatever you want to call them. Overview. Okay. Now, what can you do with them? The first thing that you can do with your roots or radicals is do the most basic thing, which is to estimate or approximate. I'm using these two phrases, sort of distinguishing one from the other, because your textbook does that. Now, when you estimate a radical, that means basically you're doing it, trying to find a solution or an outcome. It would not really be appropriate to say that. The answer, basically, answer without a calculator, right? When you're approximating, then you're trying to get the answer with a calculator. All right. When you're doing it without a calculator, just sort of save this for right now. You're trying to basically use your reference. So whatever square root that you're given, you're trying to figure out essentially what is the one that you are given between. Right, that's basically the strategy. Between what and what. When you're using a calculator, you're just pressing buttons. Now, normally what that means is that there's a button on your calculator that looks like this. Right? And then maybe you're rounding the answer. You're rounding to a specific place value. On our calculator, the type that is useful in this class, let me show you what you have here. You would have to, on this model of the Texas Instrument calculator, you would have to press second and then the x squared button to get, I'm sorry, it's a little bit blurry, to engage that sort of lighter blue square root checkmark box thingy, the operator that is square root. All right. Just above that, you may notice that there is this one that has a little x tucked into the position of the index, right there. That basically is allowing you to choose any type of radical that you want. Right? So if you wanted to do cube root or something beyond that, you can. You have the power to do that. Here, you would have to press that first. Let me just show you. This is a little counterintuitive because the screen is not so large, but if you wanted this to be a cube root, you would have to press 3 first, then you would hit second, and then this caret symbol, the upward pointing arrow, to engage the index x. It's understood that the number that you pressed first, in this case 3, that is the index that is really there, and then this would be the cube root of a, which would be 2. Right? In this class, you probably won't even have to do that. Right, you just basically start with pressing second and then x squared to get the square root symbol behind it, and then you put whatever you want in here. So if it was 4, all right, you know it's going to answer you 2. Some calculators have a button like this. All right, ours has a button like, it's 2 buttons. You'd have to hit second first, ironically, and then this figure, x squared, because this engages square root. Okay. Anyhow, that's the way that your textbook seems to prefer. They use the word approximating when they're having a calculator do the work for you, versus estimating when you're doing the thinking, right? You answer without a calculator. In which case, you're really trying to figure out, well, what is this thing in between? All right, we're going to do a couple of examples of each of these. All right. What is arguably a better thing to do is not to estimate nor to approximate, right? It is this slightly trickier, but still a better answer to a mathematician. Simplifying. Right? You can simplify roots of radicals, right? And this is basically taking advantage of this idea of factoring. Which, as you'll see, is basically something called the product rule of radicals. In a nutshell, if you are given some figure, whatever it is, some expression underneath the square root, according to the product rule of radicals, which is really factoring, right? You can break it up into 2 pieces. Perhaps one of these 2 things that you factor it into can escape the radical. That's really the strategy. Maybe one factor escapes the radical. Right? The benefit of simplifying as opposed to estimating or approximating is, in fact, that this is the exact answer. It is not admittedly the most satisfying answer, and that's why people tend not to do this. You know, they'll gravitate towards their calculator instead. But these answers that are estimates or approximates, they're not the exact answer. These are not exact, right? They're just very close guesses. Right? Make that distinction. I know that we are basically conditioned from little kids to go, the calculator is God, and whatever it tells us, it's correct, right? But it's not, right? Simplifying expressions would preserve all of infinity, which, even though, again, it's not satisfying to us humans because we're so taught to believe in the calculator and to like decimal places, right? This is actually a better answer if you had to involve this in a calculation, say in engineering or in physics. Right. All right. Now, what you could also do are these things. You can add or you could subtract radicals. Right? They have to be like, though. And what qualifies something as being like is that they have to be the same index and they have to be the same radicand in order to legally add or subtract them. Okay, so what identifies the type of radical and the guts, basically, they have to be identical. I'm not saying that this has to match this, but they have to match each other, whatever two things that you're trying to add or subtract. Right? They have to be like. Right? We'll see some examples. The only thing that you actually add or subtract, you only combine the outside, the numbers in the outside. So let's just call them coefficients. Efficients. Sorry, this is messy. Only combine the numbers out in the front of the radicals, right, that are adding or subtracting. Right. What else can you do? Well, you can multiply radicals. And in that instance, the one condition that has to be met, at least initially, is that they have to be the same index. You're not going to get too complicated a type of problem. But if they're the same index, right, then you can combine them. All right, this is more or less the product rule in reverse. All right, you'll see some examples of that. And the very last thing is this. You can divide radicals. There's really two kinds of division, though. There's more of a literal type, and again, these also have to be the same. They have to be the same index before you attempt to combine them. And then you employ jumping the gun here. So same index. You can employ something called the quotient rule. And the quotient rule is remarkably similar to the product rule. It's just sort of oriented up and down rather than left and right. There is a second type of division which is important, which is, it's called rationalizing a denominator. Here's a new one. Okay. So that is an overview. Rationalizing a denominator is basically at this stage in mathematics history, it's really more out of respect for etiquette. Right? because we have calculators that can handle anything, right? But it is practical also, right? Basically, the reason we do this is that we don't like a radical in a denominator. No radicals in a denominator. Okay. So we will rearrange an expression so that does not occur. All right. So we're going to start with estimating, approximating, and simplifying, and then we'll do the operations, basically. Adding, subtracting, multiplying, and dividing. Okay? That's the plan. All right. So let me erase this, and then we'll continue. Let me do myself a little favor here and partition the board here so that I don't have to erase everything. I'm going to make 3 columns here, and I'm going to do the same problem 3 ways. All right. Suppose you had this problem. Suppose you were given the instruction, estimate the square root of 20. Let me see if I can get the glare down a little bit. That's a bit faint. Use red because red writes the best. Estimate the square root of 20. Approximate the square root of 20. And then finally simplify the square root of 20. You'll see how these are different answers. They're remarkably similar, right, but they'll never be exactly the same. At least they're not too close. All right. If you were going about the process of estimating, if that is the instruction, again, this is the idea. What you want to do is conceive of what the square root of 20 is in between. It's between what and what in our reference. If you start with the number 20 itself, what number is the number 20 in between, the whole number 20? And by reference, I'm referring to basically this piece of paper. All right, if you were to analyze this, wow, that is really blue. What number is the number 20 in between? 2 numbers. Looking at the purple 1, 4, 9, 16, 25, 36, 49. Which perfect squares is it between? $20 would be in between the perfect square 16 and the perfect square 25. So just following this train of thought, if that is the situation, all right, the square root of 20 would be in between what and what then? The square root of 25 and the square root of 16. All right, remember that these are perfect squares, so their dimensions would be whole numbers. We're talking about area in the literal sense, right? What is the square root of 16 by itself? Trying to get out of the way here. What is the square root of 16? The principal square root, anyhow, is 4, right? What is the square root of 25? It's 5, right? So if you had to make an educated guess, right? If this is 4, a whole number, and this is 5, and this is a figure that has to be in between these two, what is exactly in between them? Right? Think of it in terms of a decimal. One would guess that this is about equal to 4.5, because 4.5 would be exactly halfway in between this and this. And that would probably be okay. I mean, like, they might specify, well, estimate to the 10th place, which would be 4.5, or estimate to the 100th place, which case you'd have to be 4 point something something, 2 spaces. This is sufficient, right, for an estimate. Now, one thing you will see, if you tested the theory and you took 4.5 and you multiplied 4.5, what you're going to notice, whether you do this by hand or you use a calculator, is that it's never going to be correct. Right? It's overshooting it. It's remarkably close, 25, right? But it's too much, right? So before the advent of calculators, what would a person do? If they kept playing this game of trying to make better and better educated guesses, what they would do is they go, well, 4.5 is too much, right? So then they'd make another guess. They'd say, well, maybe it's 4.4, right? If 4.5 squared is 20.25, and that is too much. Now let's try 4.4. And what you will notice in that instance is that it's undershooting it. It's too little. Right? Here's 4.4 squared. 19.36. So then a person would go, well, that's too much and that's too little. So what I'd have to figure is, what is exactly in between 4.4 and 4.5? If this is 4.50 in essence, and this is 4.40, what would be exactly in between these? What's between 40 and 50? 4.45, right? What would 4.45 be squared? What you'd see is that you're inching closer and closer to 20. You get 19.80525 rather, right? 19.8025. Now here's the thing. You could keep doing this for the rest of your life and you're never going to reach 20. What's going to happen is that you're just going to have a greater and greater degree of precision. You're going to inch closer and closer to 20 but never reach it. All right? Why? Because it is an irrational number. And irrational numbers are infinitely stretching, so this is futile, this exercise. All right? And they don't have a pattern. All right? So you can't write this as a fraction no matter what you do. All right? And you could just make better and better guesses. That's what a calculator does. A calculator makes very good educated guesses instantaneously because it's programmed to do that. All right? Anyhow, unless they specify some other place value, 10th place is perfectly sufficient for an estimate. It's about 4.5. You could see it's very close. It's 20.25. All right, continuing. Now, if you use our model calculator to approximate the square root of 20, you'll see how precise you can get it, right? What you would have to do in our case is you would have to press the second button and then the x squared button, because in tandem these two things engage what is written in blue behind it, the square root. All right? And then you write 20 in here. What do you see on your screen once you do that? If you hit, sorry for the glare, second, and then x squared, again engages this square root checkmark operator, and then you press 20, and then you could be a good sport and close the parentheses, but it's understood. And then you hit equals, look what you have, 4.47572135955, right? Just realize that although this is very precise, 4.472135955, that's where it ends, right? On your calculator screen, but in fact the number goes into infinity, right? That's the degree of precision that your calculator has. 10 decimal places, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Let's see what would happen if I squared this. Would you actually get 20 if I squared it? If they made the calculator correct for that, then perhaps it would, but maybe not. Answer: it does. Only for the reason that your calculator can round up, basically. Right? This is kind of how you can tell the difference between a good $20 variety calculator and a crummy $5 special calculator. The $5 special calculators, they don't factor in the fact that they have to round up to produce the actual number. Right? They're not that correct. They're not as good. Right? Anyhow, usually what would happen in the classic case is that they say use your calculator to approximate and then round to, say, the hundredths place. So the hundredths place, hundredths, is where the 7 is sitting. Based upon there being a 2 here, you would knock off infinity and you would say that this is about 4.47, right? My educated guess is pretty close. As a matter of fact, it would round to the tenths place that way, but it's still not exact, right? Is the bottom line. Now, if you were going to simplify, this is the process, right, that you want to go through. You want to factor this number 20, right? This is really something called the product rule. And to that end, what I should do is discuss this other piece of paper. The ideal situation is described on this piece of paper. When you're factoring radicals, the ideal situation is that you want to choose two numbers that are being multiplied. Basically, the guts of the radicals is what you're looking at. And in the first one, you want the highest perfect square that is possible. All right. If you were dealing with a cube root, then you would want the highest perfect cube that is possible. You're not going to really see that too much in this class. The other thing would be, in theory, a prime number, or if it is a composite, it would be a composite number that would be impractical to keep factoring. And you'll see what I mean in a moment. All right. So, this is the product rule. The product rule of radicals if you have something that is underneath the radical symbol, then you could break it down into two things being multiplied. All right? Ideally, again, you want the highest perfect square possible. If you do, we'll get to the answer much quicker. There is something you'll see momentarily, a quotient rule. I'll come back to it, though. All right, so in this case, for a moment, I'm going to list all of the factors that make 20. All right? 1 and 20 is a pair of factors that make 20. 2 and 10 is a pair of factors that make 20. And 4 and 5. Right? Now, as you can see from this list, that there's more than one perfect square that coincidentally shows up in here. And if you're a little bit sketchy about the perfect squares, remember you have a table of them. These numbers, 1, 4, and so forth in purple, are the perfect squares. 1 is in fact the perfect square, but we want, ideally, the highest perfect square that is possible. And in that case, it would be the number 4, right? Rather than the number 1. 1 is not going to change much. So if I'm factoring 20, I can make this 4 times, what would the other number have to be? What times 4 makes 20? 5. The benefit of doing this is that even if you can't make the radical go away entirely, then maybe what you can do is have one of these escape. What is the square root of 4 just unto itself? That is 2. So if I were going to write this as a simplified incarnation of this, that would be the answer. 2 times the square root of 5, right? And it is arguably a better answer than to leave it as the square root of 20, because now you've expressed the exact same quantity, the irrational quantity that stretches into infinity with no perceptible pattern, using the smallest numbers possible. That is better because this is an exact answer. It isn't immediately satisfying to us humans because, again, we're used to making a calculator do something. We're used to making an educated guess. A decimal makes us feel warm and fuzzy, right? But here's proof that these are the same thing. What is the square root of 20? From before, we have it to this extent here, up to the edge of the screen here, 4.47 something. If my answer is correct, 2 times the square root of 5 is in fact a simplified incarnation of square root of 20, you'll see the same answer on the screen. All right? So here's 2 times the square root of 5. And there you have it, 4.47 such and such into infinity. This is a better process. It's hard to convince people. It's very hard to sell to a little kid, especially because, again, we were all taught to bow down to the god that is the calculator. All right? But, all right, don't knock a human mind either, right? This preserves all of infinity. And therefore it is an exact answer, even if you don't get the satisfaction of seeing infinity, which is a futile effort, right? Something that stretches into infinity, you know, that old adage, on a clear day you could see forever. Technically you can, right? You can't really enjoy it though, right? These are the answers that we had done, estimating and approximating, whether you did it in your head or you did it with a calculator. They're chopping off infinity, right? So they're not really correct. They're not exact. All right, now, this is the product rule. It's for factoring. All right. And in theory, there is a quotient rule as well. It's the same idea. If you had something that was oriented like this, basically a fraction that was underneath a radical, if it is a convenience for you, the quotient rule says that you could break it up into 2 independent pieces like this. Because, again, maybe one or the other will escape the radical. And therefore you can simplify. All right. Let's do another one of these simplifying types of problems. I need the space. Here is another. Suppose we are going to simplify rather than approximate the square root of 80. Right. Now let me show you what happens. Normally what happens is that a person may do it one way or another, but whether you choose to factor something, it's sort of like factor trees. one way or another. The end result has to be the same, and it should be the same as long as you're careful. All right. Let me do what is the ideal situation. I'm going to opt for the highest perfect square that is possible. All right. When it comes to listing all of the pairs of factors that make 80, it isn't that easy because of the nature of the problem being a double-digit number, but you can figure it out. So just for the sake of space, I'm going to write them up here. There's always the easiest one, 1 times 80, right? And then it's an even, so it's going to be 2 times 40. It won't be divisible by 3, so therefore 3 is not a factor, right? But it would be 4 times 20, right? And it ends in a 0, so it's divisible by 5. And it would be 5 times what? 5 goes into 8 one time with 3 left over, it would be 16, right? And then 6 is not going to be a factor because both 2 and 3 would have to be factors, and it's only 2, right? 7 times 10 would be 70. 7 times 11 is 77. That's too short, right? And then it would be 8 times 10. Okay. And that's pretty, once you start from as far apart as you possibly can, 1 and 80 are very far apart. You notice that if you go down this sequence, you'll get to 2 numbers as close as possible until you overshoot them. So this is pretty much a comprehensive, complete, thorough list of the pairs of factors that we have to choose from when we're factoring 80. I again want to choose the highest perfect square possible because this is a square root. 1 is a perfect square, right? It appears in our list of perfect squares, right? But it isn't the highest one, and it really, you should never use 1 because it's not really going to get you make any progress. You're going to get stuck with 80 again. 4 is a perfect square, and you might just go that route. But what is actually the highest in this list of possibilities? It's 16, right? So this would be the square root of 16 times what? What does it work with in tandem? 5, right? What is the square root of 16 by itself? It's 4, so therefore this is 4 times the square root of 5, right? That is the answer, right? I would bet that a person who is not too familiar, a little bit unsure of themselves, would maybe try 4 instead, right? And if you did, there's no sin in that, but you're going to realize that you're going to have to make sure that you get the same answer in the end. So I'm just going to show you that train of thought in case you go that route by mistake, all right? It will work. It's just going to take a little bit more brute force, right? Maybe even if you did something like 8 and 10, all right? Maybe that would be better. 8 and 10. And you go, well, can I factor this? Can I factor this? Yeah, you can factor down 8 into 4 and 2. And remember you'd have to keep them in square roots. It's not just factor trees in the normal sense. And then you would factor down maybe 10 into 5 and 2. And look what you have here. You have some similarity. You already see that there's a square root of 5 here. And you do have one thing that is, you might recognize, oh yeah, square root of 4, good. All right. So you would go, that thing is 2, all right? And that escapes the radical. That is progress. But look what you have left over. You still have this other junk left over. I'm going to put them in order here. You'd have square root of 2, and then another square root of 2, and then another square root of 5 here, all right? Now, according to the product rule, if you start with something like this, you can break it up. But in theory, if you needed to, you could go backwards and put them together. As long as they are the same index, legally speaking, you can do that. So if you recombine these two, what would you end up with? You would end up with the square root of 4 again, right? Because 2 times 2 is 4. And then you would go, oh, wait a minute. The square root of 4, just like as it was before, all right, is itself 2. And so you would have a 2 here and a 2 here. And then that square root of 5 still hanging on for dear life over here, right? And even though that is correct, it isn't really simplified. So what you could do is merge together the stuff that is now on the outside. And you would end up with the same thing. The leftover 2 is 4 on the outside, square root of 5. The bottom line is that you will get to the same answer if you stick it through. And it is hard to convince a person, especially if they lack experience, to go, okay, you're on the right track, right? They may not know when to stop, right? That's why I think this is a better situation. To convince a person, ideally, you want the highest perfect square possible. You're pretty much done in 2 steps. Okay? Now, moving along. Let's add or subtract now. If you are going to add or subtract radicals, right, they have to be like, really. Which means that they have to be, firstly, the same index, the same type of radical, and they have to have the same guts, right? They have to have the same radicand, right? I.e. the guts. And the only thing that you actually combined is the outsides. Only. Here's an example. If you had 5 square root of 3 plus 4 square root of 3, let's just make sure that these are like, first of all. Are they the same index? They would technically both be square roots, right? There's never going to be a 2 here and here, but I'm just doing that to make it more clear, all right? Are they the same guts? If you look at the inside of the radicand, the inside of the radical symbol, do they have the same guts? That's a 3, that's a 3. They're good to go. So what are you actually going to combine? You're going to combine the outside only. That means, essentially, that you are just treating this as if it was a letter X and this was a letter X. So what's 5 plus 4? It would be 9 with a square root of 3 attached to it. Okay? What if you had this problem instead? What if you had something slightly more complicated? 2 square root of 5 minus 6 square root of 5 plus the square root of 5. Right? As always, when you're dealing with expressions, and you notice there's no equal sign anywhere in here. Right? If there's no equal sign, then you're dealing with an expression. Right? So you simplify expressions, however complicated or long they may be, using the order of operations. Now what I would do is still be careful, all right? Analyze the radicals, otherwise don't bother subtracting and don't bother adding. Are they the same index? They're all square roots, right? Do they have the same guts? The same radicands? They're all 5s. So you can actually perform the operation. Now, which one do? You have the choice between subtracting and you have adding. According to the order of operations, adding and subtracting are equally important. They're on the same tier. So which one should you actually do? You should do these merely for the reason that we read left to right. And these are on the left. Do leftmost first. All left. So what do you actually combine? You're just combining the outsides. Now, you do have to employ rules for signs. Oh, here we go with the fire again. Sorry. I have a sneaking suspicion that the maintenance people, pardon me, the construction crew who are renovating next door are smoking, and they keep setting off my smoke alarms. All right. Anyhow, there's something I could do about it now. What was I saying? Well, in addition to having to follow the order of operations, this is when you're simplifying expressions, and this is just one big expression. What you have to do is also use rules for sign combinations. When you're adding and subtracting, you know, there's a set of rules. All right, now, my focus is really just here and here for right now. I'm completely ignoring that. This is a positive, and this is a negative. So when you have one of each sign, remember that you have to subtract actually. So 2 minus 6 would produce a 4 for the magnitude, and it would have a 5 attached to it, square root of 5. And the sign of the answer is going to match the larger magnitude, distance from 0, so this is a negative 4. Okay? Simultaneously, there is this 5 that's hanging on here, so I'm going to just put it here, plus square root of 5. If there's no obvious number written here, what could you assume that it is? It is a coefficient, technically, right? A number. It's not really a coefficient because there's no x here, but you can kind of think of it like a coefficient. So it's a 1, really. And then you do the same thing. If you have to decide, you know, how these are going to be combined, is it adding, is it subtracting? You have one of each again, so you're really going to subtract, which means that the digit is going to be 3, right? And the sign of the answer is going to match the larger magnitude, which again in this case is still the negative. So it's negative 3 times the square root of 5 attached to it. Okay, now let me just make some space here. What if you had this situation? We had pieces of wood here. What if you had to combine 5 square root of 3 minus 12? Pardon me, minus the square root of 12. Right? Now, a person who lacks experience might look at this and go, well, are these like, which is a good thing to check. Are they the same index? Yeah, they're both square roots. All right. Are they the same radicands, though? Are the guts the same? The guts here are 3 and the guts here are 12. All right. So you go, no, they're not really like. All right. And the person might go, well, that's it. I'm done. And move on with your life. But don't give up, right? What you might notice is that it is possible, right, when they're unlike, right, try to factor, right, use the product rule, essentially. Before you give up, try to factor. Now, think of the things that you could factor 12 into, and here are the factors of 12. 1 and 12. 2 and 6, and 3 and 4. Opt for the highest perfect square that is possible. All right, 1 is always going to be a perfect square involved in everything, but 4 would be the better choice. So you have 4 times the square root of 3. right? And if you do that, now what do you get? What's the square root of 4? 2 square root of 3 left over, right? Which means, in fact, this is 5 square root of 3 minus 2 square root of 3, which means they are, in fact, like the same index, and now they have the same radicands. They're both 3's. So if this is positive 5 and this is negative 2, right, one of each again, you subtract them, you get a 3, and it ends up being a positive in this case. 3 square root of 3 is your answer. All right. Let's do a multiplication problem for 2. It's warm today. I need water. Okay. I'm sorry, I'm wearing a shirt that is apparently way too short, and it keeps pulling out of my pants. All right. Where was I? Okay. Multiplying, yay. All right. Now, when you're multiplying, just to remind you, radicals. All right. What you need in this stage is to make sure that they're the same index. Right? If they're the same index, then you can immediately combine them. Right? It's more or less the product rule in reverse. So as an example, suppose you had square root of 3 times the square root of 27. Right? They're both square roots, therefore they're the same index. So we can combine them immediately and employ the product rule more or less in reverse. So if you combine these two numbers, 3 and 27, under one radical, that is if you multiply by 3. So 7 times 3 is 21, carry the 2. 6 plus 2 is 81, right? And it just so happens that 81 is a perfect square. So what's the square root of 81? We want the principal square root. It's 9. Okay. Let's see. Here's a maybe more complicated one. What about square root of 3 times the square root of 13? If you combine these two, that is, you multiply by 3, and you would be legally allowed to, you'd get 39, the square root of 39. I would attempt to check to see if this is a perfect square. It is remarkably close to perfect square 36. So it's not going to produce a whole number, all right? That doesn't mean give up immediately, but what you would try to do is to factor it, all right? Now, here's what would happen if you attempted to list all the factors of 39. It would be firstly 1 and 39. That produces 39. It's not even, so you can't use 2. But there's the thing, of course, that it came from, 3 and 13. Let's check if there's anything else. It's certainly not going to be 4. It isn't going to be 5. It can't be 6 because 2 doesn't work. 7 times 5 is 35. That's too short. And 8 times 5 is 40. That's too much. All right. And 9 times 4 is 36. All right. I think that's pretty much exhausted. It's a composite number, but it only has these two pairs of factors, evidently. 10 doesn't work, 11 doesn't work, 12 isn't going to work. All right? So the only perfect square that it has to choose from would be 1. And if I attempted to factor this into the square root of 1 and the square root of 39, that's not really making progress. So this one, you're basically stuck with it, right? Right? That's it. It is as simplified as it's going to get, right? If you had instead this problem, square root of 6 times the square root of 10, again, if you combine these, they're the same index, you can do that immediately, all right? Then what you get is 60, right? And you might go, well, that's pretty intimidating, so maybe I'm done with that. No, don't give up hope immediately, right? You could try to figure out all of the factors of 60. I know it's a little tedious, but it isn't impossible. It'd be 1 and 60, 2 times 30, 3 times 20. Really pay attention to the non-zero to figure that out, right? 4 times 15, which you might recognize from quarters of an hour. 15 minutes times 4 is 60 minutes, right? You know your times tables of 5 times 12, all right, and 6 and 10 is what it came from. Then you could verify 7. 7 times 9 would be 63, that's too much. And 8 times 7 is 56, that's too little. And that's pretty much it. You've exhausted all possibilities. All right, started far away and you approached close to each other. All right. Now look for the perfect square, all right, in this list. 1 is always going to be perfect square, but we never choose that option because it's lousy, right? 4 is a perfect square, but let's just check the other ones. 15, nope. 5, 12, Well, it looks like it's going to be square root of 4 times the square root of 15, right? In which case, what's the square root of 4 again? It's 2 with a 15 attached to it. If in fact you have chosen the highest perfect square possible, you're probably done, but I'm just out of being anal retentive here. If you try to factor 15, it would only go down to maybe 1 and 15 or 3 and 5. And in that instance, that's what I was getting at before. I said this in the instruction. I said you might end up with a composite number here. But if it is in fact a composite number, it might just be a composite number that would be inconvenient to factor any further. 15 is an example of that, because if you were to factor it any further, you're going to get stuck with things, no matter what, that are not going to escape the radical. Neither escapes the radical. So if that's the case, then that's pretty much it. It's 2 times the square root of 15. Right. It's not simplifying if they don't actually lead. All right. Let's get into dividing, and then we'll do rationalizing, and then we're done. It's very nice, that one. Is this the terrible one that doesn't erase? Yes, I think that might be it. Oh, now it's behaving. Okay. All right. If you were dividing radicals, really what you just have to be aware of is that there's a quotient rule or a quotient rule. They have to be, again, the same index, but you're probably not going to have problems that you have to really worry about that. If there's the same index, right, then you can combine them if necessary. All right. More likely what you're going to do is you're going to employ the quotient rule for radicals, which says that if you have a fraction-esque looking ratio here, both of these things underneath the radical symbol, if it is a convenience for you, you could break them up into 2 separate radicals. Right? what you want to avoid, if you can help it, is try not to leave a radical in the denominator. Right, that's considered bad etiquette, essentially. Bad etiquette. I know that is, I'm trying to be funny, really, when I say that, because there's no such thing as etiquette in the math world, but it's just for appearances that we don't do that, right? Years ago, there were no calculators, and having a radical in a denominator really complicated a person's life. So what we would do, is we would attempt to, in this situation, rationalize the denominator. And what that means essentially is rearrange the problem so that there isn't a radical in the denominator. All right, there's some techniques for that, but I'll get to it in a moment. All right, you're not going to have to worry about it immediately. Let's do this first. All right. And if you had this as an example, the square root of 75 over 3. Pardon me. The square root of 75 over the square root of 3. Two separate things, two separate radicals. Right? In this case, it would be sort of the quotient rule in reverse. If you have two separate radicals, you can recombine them, if it is to your advantage. Right? Why would a person do that? They might recognize that, well, there's a relationship between these two numbers that is familiar to me, a human, intuitively, who lives in the United States, because we deal with coins that are of 25-cent denomination. I could recombine these into just 75 over 3 under one radical. And then if it happens to divide, that 75 is divisible by 3, it divides nicely. And what I can do is just reduce this to 25, which, lo and behold, is a perfect square. The answer is 5. Right? You don't always have things that work out that nicely, but this is engaging in some sort of mental agility. Shifting your focus from breaking something up or recombining it. Right? Factoring or unfactoring, for lack of a better phrase. I don't want to erase that just yet. So let me use a bad marker. Not a mess. All right, let us try this problem. Which one is the lousy one? Suppose you had the square root of 60 over the square root of 5. Right? We'll try the quotient rule in reverse, right? Perhaps it is to our advantage to combine these. Right? If it was 60 over 5, they're the same index, so legally speaking, you could immediately recombine them. Right? What does 60 divide by 5? It would be 12, right? And then what you end up with is something that is factorable. So what's going on here is it's the quotient rule in reverse. And what will happen next is that we will employ the product rule for the sake of factoring. So what could you break this into? 4 times the square root of 3, in which case you end up with Square root of 4 is 2 again, square root of 3. This is exact, preserves all of infinity. It would produce the same exact decimal as this. The original and this should produce the same decimal. Okay. Now, let me give you a little bit of strategy here for when you're rationalizing, right? For those situations where you get stuck with a radical in a denominator, and that's really, again, bad etiquette at this point. It's also not practical if you had to combine this, like say you were adding radical expressions that have a fraction somehow. Here's a strategy. Strategy for rationalizing the denominator, right? The situation, primarily what you will be responsible for square roots. What I'm just going to say in general, square, cube root, etc. What you will try to do is basically multiply by a convenient ratio of 1 in either situation, right? If you're trying to do it for square roots, what that usually means is that the convenient ratio of 1 is going to be the denominator over the denominator, right? If it's just in general, the convenient ratio of 1 can be any number over itself, but you would try to incorporate a factor that promotes a cancellation effect. Now let me give you an example and you'll see what I'm getting at here. This process is basically rewriting a problem so that there is no radical in the denominator. Right? Rationalizing a denominator is essentially that. So here's an example, right? That's more in tune with specifically the situation where you're just going to borrow whatever the denominator is and write it on top of itself, right? Suppose that you had 5 over the square root of 2. Here's square root of 2. It came back. Right. What you want to do, again, is basically this in any situation. You want to multiply by a convenient ratio of 1. I'm saying convenient because it makes things work well, right, to your advantage. So, for example, here is the number 1. Do we agree that if I multiply anything, even something ugly, times 1, that it's going to basically preserve the identity of that thing? That it's not going to change the value of this overall. If I just multiply by 1, that would be true, right? So therefore, what I can do is try to write the amount that is 1, but more or less disguise it, you know, in a convenient ratio. What does that mean? It means as something in the style of a fraction, right? Something over itself overall is still the amount of 1. It's just disguised, essentially, all right? In the case of square roots, what that usually just means is figure out whatever the denominator is to begin with, and then just borrow that. Square root of 2 over square root of 2. Square root of 2, granted, is famously an irrational number, 1.41, whatever it is, into infinity. But even if I don't know what all of it is, it's still something divided by itself. So what is it equal to? It's still equal to 1. So legally speaking, it might seem like I'm just ripping numbers out of midair here, but I could legally get away with it because it's still the amount of 1 overall. It's just disguised. It's a convenient ratio of 1. And the benefit of that is that now what I have is 5 times the number square root of 2 on top. And then on the bottom is the square root of 2 times the square root of 2, which is the square root of 4. And what's the square root of 4 just by itself? It's this. It's 5 square root of 2 above the line, and just sad, lonely, regular number 2 underneath the line. It is rationalized. I've rewritten the original expression in blue, now in red over here, so that there is no square root in the denominator. I'm doing that more or less as a habit of good etiquette, but the truth of the matter is, if you weren't dealing with a calculator, and you had a square root in the denominator, it's cumbersome. So it really is to your advantage to write things this way, even if it seems silly. All right? Now here's proof that they're the same thing. All right? I use the calculator for the little that I can. The decimal of the original expression, 5 divided by the square root of 2, is this value, 3.5 something. All right? If my calculation simplified, or maybe arguably not simplified, the rationalized expression is in fact the same quantity, and it ought to be, then the decimal equivalent would be 3.5 something. So let's see. All right, 5 times the square root of 2 divided by 2. I'm being extra careful and using a lot of parentheses here. 3.5 something into infinity, right? Correct. Right. This is referred to as a rationalized expression. Right? It's basically rewriting the original expression so that there's no square root in the denominator. Just a regular whole number. Just a regular 2, rather. All right. Now, I'm making a separate sort of paradigm here. I say in general because sometimes you guys probably not in this class. You want to have cube roots and stuff like that, but when you are doing this, the real goal here is that you're trying to promote some kind of a cancellation effect. So if you had a cube root in theory, you'd have to be a little bit smarter than just simply replicating the denominator here. Right? That will get you only so far with a square root. That only works with square roots, just imitating what you see here and here. All right. I'll give you a couple of problems and you'll see what I mean. You could be a little bit more strategic, right? And that is really what I'm referring to here. Try to be more strategic. Do whatever it is. Incorporate a factor, whatever you need to promote a cancellation effect. Here's a slightly trickier problem.
Okay, so I have your page open. This is going to be right. It's going to be, let me just quickly verify you first.
Right. I'll do the same problem 2 different ways. Here's the example. We're going to pull the same trick that we just had done. Right? Here you have 5 essentially divided by the square root of 12. Now, notice that this is a radical 12 and this is not a radical, it's just regular numbers. So we can't really use the quotient rule here at all right? But we can rationalize. So following a separate train of thought, a different paradigm, what I'm going to do is essentially this. I'm going to take that expression, 5 over the square root of 12, and again, do this. Multiply by some convenient ratio of 1. Right? And what that usually just entails doing is borrowing whatever the denominator is here. So if this is square root of 12, I'm just going to write square root of 12 over the square root of 12. it's an ugly figure, right? It's an irrational number. Whatever decimal it is, whatever decimal it is. But overall, this is still equal to 1. So legally speaking, it's going to change the appearance of something. It will affect the aesthetics of it. But it's not going to change the actual value, right? So top times top means that you have 5 square root of 12, and on the bottom, it's sort of the product rule in reverse. 12 times 12 is the square root of 144, right? What is the square root of 144? Right? It is a perfect square, which you may or may not know, but it is. So you would get 12 as a denominator. Hypothetically, there's an alternative way of writing this, right? If you just wrote it as the square root of 12 squared, because it's a clone of itself, really, they could put that 2 as an abbreviation. The effect is still the same. This is an opposite operation of that, right? And would expose the guts here, 12. Right? Anyhow, this is the answer. 5 times the square root of 12 over 12. It is now rationalized. All right, and arguably better, even if it looks like it's more complicated than it was. There's no radical in the denominator. You know what? The truth is, you can go a little bit further with this. I mean, this is correct, but it just so happens, in this case, that what is left over up here, we did this before, right? That could be factored. So this could be square root of 4 times the square root of 3, right? What's the square root of 4 by itself? The square root of 4 is just 2. So outside 2 times outside 5 is really what? It's 10 square root of 3, and then there's a 12 underneath. And if necessary, you're just looking at that as if it was an ordinary fraction, 10 over 12, you might recognize that that is itself reducible. All right, it's simplifiable. What are they both made of, the number 10 and the number 12? They're both even, so they're definitely made of the number 2. So I could divide this and this by 2, and that would be a 5 here, and this would be a 6 here. That means that the answer to this problem is best written like so. 5 square root of 3 over 6. This is simplified completely.
Yes, just make sure everything is filled out. If they ask for a driver's license, make sure it's up to date.
All right, it's rationalized, and the figures that are left over are as small as they can possibly get. 5 times the square root of 3 over 6. Now, here is the other train of thought, the other paradigm, if you will. When you're looking at the problem this way, 5 over the square root of 12. I'm still going to basically employ this basic idea. I'm going to multiply by some convenient ratio that is equal to 1, right? But instead of simply borrowing the 12 that is there, I'm going to try to sort of upgrade to a perfect square. 12 itself is not a perfect square, right? But, right, if we go to my list of perfect squares, where you have it memorized, you might recognize a number in this list of purple numbers, 1, 4, 9, 16, 25, 36, 49, so forth, that happens to also be a multiple of 12. In other words, you know not just the perfect squares, but you also know your multiplication tables, right? This is why I don't mean to be, to sort of belabor the point. But you must, in the position of teacher, defy your bosses. If your superiors tell you, don't make the kids memorize the multiplication tables, forget that they ever told you that. All right, it is so wrong. It is hobbling a child not to get them to exercise that most basic way that we learn, which is to memorize. If you know your times tables, you could be strategic. All right, it's a frame of reference that you are storing in your mind. All right, be open to obviously different methods. That's a different story. But never exercise one skill in lieu of another. It's better to try to cultivate as many skills as possible. Is what I'm getting at. Anyhow.
what number can I multiply 12 by with the intention of making 36, just because 36 is a multiple of 12 that happens to be a perfect square, right? It's multiplying by 3, right? So maybe I'll just change the color for a moment. Square root of 3, right? Now that's not just simply borrowing the thing that is here, but I could still, as long as it's square root of 3 over square root of 3, I could still utilize this as a convenient ratio of 1. Right? It's something over itself, which overall is still the amount of 1, and therefore it's preserving the identity of something. It's just changing its appearance. All right? So 12 times 3, product rule in reverse is 36, so it's the square root of 36. On top, it's 5 square root of 3. Anyhow, what is the square root of 36 by itself? This unto itself is just 6, right? So that is the same answer. It's just being a little bit more crafty to get to the answer. Right? As is often the case in math, there's more than one way to do something. If you try to expose yourself or whoever you're teaching to the infinite possibilities, then you're doing your job. All right? You're building mental flexibility, right, to be able to see something in one way or another. It still gets to the same result. All right? Granted, there are some things that are just more efficient, all right? But you gotta, if there's one thing you should do with a math student is just go slow, right? I know we don't always have time, but tell them that we're gonna get to the answer no matter what, right? And as long as they develop a level of comfort, they will eventually get it. They will eventually get the answer, right? You got to make somebody comfortable. You got to take their fear away from them. That's the resistance that you're going to be met with as a math teacher. People are afraid. All right, one more of these and then I'll stop. What is familiar is less scary, is what I'm getting at. You empower, when a person finally realizes that they can do something, they are empowered, right? And then they are less afraid. And that has a snowball effect, I've noticed, right? Give them security, you know? Develop it in yourself, right? I know we're not born feeling secure, but that's the goal, right? So here we have this. These are both square roots, so the quotient rule would be a viable option here, right? It would be the quotient rule in reverse. So I can recombine these, and if I do, what do I end up with? I end up with 5 over 10, right? Then I can reduce this as a fraction, right? The inside guts here. It would be 1/2, right? At this stage, I can then employ the quotient rule to factor it, essentially. Right? And that would be the square root of 1 over the square root of 2. I would pull the trick from before, in this case, just to simply rationalize the denominator. Just because it would be less complicated, all right, not having a square root in the denominator. So the convenient ratio of 1 in this case is just to borrow the denominator of 2, square root of 2. These two would essentially cancel, and then the top would be the square root of 2, right? You could, if you wanted to, you could figure out the square root of 1 by itself as just 1, but you're going to end up with the same result either way, right? The effect is basically this. Whether you chose to go this route and say, well, it's 4 by recombining them, or writing it from the perspective of exponents, which is to say, well, there's 2 clones here, so I can abbreviate that as the thing squared. These are opposite operations. That's the cancellation effect that I'm alluding to. Opposite operations cancel each other. So the bottom line is you're left with this, square root of 2 over 2. All right. All right, that is everything. We're over 2 hours here. So let me put this away. Print the references. I really think that's the best thing for now, especially if you don't have things memorized. In the long run, you want to strategically memorize certain things. All right, and that's it. For homework, you want to do section 5.4 in MyLab. Now, you may have noticed what I did was I opened up the remaining assignments from now until May 4th. So this next batch will be due May 4th, right, the day of the third test, right, just like before. Okay, all right, so try to keep pace with that, all right, and I'll see you guys on Tuesday, all right. Be careful out there.